I'm going to perhaps continue the work that Juan Cruz talked about. He talked a lot about simulation in reentry, descent, and landing. Talked a lot about probability and statistics, and even mentioned Monte Carlo simulation. And if I had the dice, if I was allowed to hold the dice, I would show you that you could even use them to do some simulations as well. I'm going to talk about it from the point of view of structural mechanics, modeling simulation and probability and structural design. And so, let's see, I've got to figure out how to do this. Okay, there we go. No, that's okay. I'll have my own show and tell in a second. This is an overview. I won't go into this too much, but I'm going to go over some very simple examples. And basically, there's not much that's around you that isn't designed or looked at in this manner. And in fact, there's a branch head here at Langley that basically says, head of materials, because you got to build out of something. And pretty much everything you got around you is either a material or a structure made from material, so we're everywhere. And probability statistics, believe it or not, underlie most of what we live with in the structural materials area. We're just not aware of it. So this will be kind of hopefully interesting to you as well. I'm going to talk about the factor of safety and how that's used in structural design, and talk about reliability. And reliability is another way of looking at probability statistics from a design point of view. And what I'm going to talk about also, I was one of last year's mentors. I think last year may have been the first year they actually had the program, and I was a mentor and had two very excellent students. And I'll talk a little bit about my experience at the end and maybe give some hints to the new mentors on what I thought worked well and what I think they thought worked well too. Okay, the first thing I want to talk about is, and this is something that we've used quite a bit in structural materials, it's called the three-legged stool paradigm for solving a problem or doing a design or pretty much everything that we do. And what it does is it's really based on a philosophy. And the philosophy, and I'm going to credit the philosophy author is Dr. James Starnes. In fact, you go around Langley, there's 3 buildings named after someone here. There's the Reed Center, which is an auditorium. There's the Pearl Young Center, and there's a Starnes Lab, Starnes Structural Materials Lab, and it's named after Jim Starnes, who was one of my mentors here, and so he was one of the. In fact, he was Juan Cruz's mentor as well. He passed away a few years ago, and one of the few people that made such a big contribution that they're acknowledged by naming a building after him. So anyway, he came up with this three-legged paradigm, three-legged stool for solving a problem. And it's integral in anything we do in modeling simulation because you've got 3 things. You've got experiments, the physics of the problem, and you can simulate anything, but unless it's got a physical basis, it's valueless. So you've got to understand the physics, and you get that by doing experiments. That's one leg. Another leg is, and you're trying to apply this to a specific concept or problem. Another leg is the analysis. You have to have a mathematical model. Juan Cruz talked about that earlier. Here I'm showing, I don't know if there's a pointer up here or not. Doesn't look like there is. Over on the right, there's a model. In fact, the experiments I'm showing you, the picture up there is one of our test machines in the Starnes lab. It's a 1 million pound machine. You can put 1 million pounds of load on a structure and crush it, or do something a little less destructive. But basically, it's a high load testing machine. We do have a lot of machines like that in the Starnes lab. We also do some more delicate experiments where we want to look at the very details of a structural response because we want to correlate those models. And so that's shown on the right side there. There's a test there showing you essentially a very simple hole in a composite structure. It's got a speckle pattern around it, and we use that with some very advanced instrumentation to look at the local stresses and strains. And we correlate that with a model. So in there on the right side is an actual analysis. So you get the test and the analysis, and we try to make sure that our analysis, our models, accurately reflect the physics. So that's an important part of the analysis part. The mathematical models have to reflect the physics. But they don't, just reflecting the physics doesn't do you any good unless you can do something with it. And that's where we have to design something, we have to build something. So the optimization design is a third leg of the stool. Okay, thank you. So those 3 legs work together in pretty much everything we do here in Langley. And this is applying it to structural mechanics, structures, but if you look at any other discipline here, aerodynamics, guidance and control, pretty much the same three legs are there in one form or another. And modeling simulation, I show the bullets in the bottom, are really intrinsic to this whole paradigm because the modeling, the mathematical models of the physical phenomena. First, see what the phenomena is experimentally, then come up with a model that actually can reproduce it and even be used in a predictive fashion. So to predict something we don't have data on. We take those and we make them to a computer model. We want a numerical implementation of them, make a simulation tool. And then we eventually develop our design using those tools. We use visualization. I think Juan showed a very good simulation showing an engineering simulation of a reentry vehicle coming in there. We do all this. This is a simulation there. That analysis is showing you kind of the delamination and the splitting apart of a composite structure. So these pieces together are all integral in modeling simulation. So it's not just computers. It's computers and reality and using them for a useful purpose, doing some kind of design. So I'm going to get into some very specific application here. I'm going to talk about something called stress and strength. Stress is a very basic concept, and it's not the stress that you get when you have to pass an exam. This is mechanical stress, and it's really defined, and I'll use this simple popsicle. In fact, the students, the teachers that I mentored last year, they did a whole presentation on popsicle sticks and failure of popsicle sticks because that was part of their they did a great job. I'll talk about that a little later. But stress is basically a very simple concept. You've got a structure. It's got a cross section, like a length, a width, and diameter. Take that cross section, essentially cut this in half, and look at that cross sectional area. When you pull on that, that force divided by the area is called the stress. It's a concept we use to understand inside a structure what is the state, the mechanical state of that structure. It's a stress. It's basically the amount of force that's trying to be transmitted over any interface. And that, I pull on it a little bit, I've got a little stress. I pull on a lot, I've got a lot of stress. Eventually I can pull on enough and I break it. Well, that's when you get to strength. Strength is now a material property. That's the bottom bullet there. It's another basic concept in structures. And so stress, you can put as much stress as you want on something, but pretty much eventually it'll break. And that's the strength. And the strength of a structure, strength of a material, is a stress that causes failure. And failure occurs whenever the stress is greater than the strength. So you pull on something until it's past its strength, the material property that says this will break, and then it breaks. But it's not an exact property. I took this one sample and broke it, and if I actually had some instrumentation on it, I could tell you what load it would broke at. But I did that again, I would get a different answer. It'd be close, but it won't be the same thing. So probability and statistics, here's one use of it, material strength. We actually will test many identical samples. So I got the first one I broke. The second one, you break that and you take your measurements. A third, take that, break that. And what you get is at each place it broke, you have a different strength, a different load at which it broke at. And so this curve here, down I'm showing here lower left, this is showing some real data, not the data of these popsicle sticks, but this is the yield stress at which something fails. And this is a histogram. So basically, if between these two values, and this is Juan would kill me for this because this is using English units instead of using SI. But this is between 41 and 43,000 pounds per square inch. In this case, 4 samples broke. A little bit lower level, we had a few more break. A little lower, in this case, a fewer broke, and then right around here, about between 36 and 37, a whole lot broke. In this case, there probably, I'm going to guess, about 60, 70 samples were tested, and this is the histogram. So basically, over each interval, this is the number that broke. Well, so that becomes data now we can use to get a material property. So you've got, essentially, you could fit this curve here. You could say, well, let's say this has one of the classical distributions, like a Gaussian distribution, which shows you essentially the frequency, and this is the left axis here, number of population, number that broke. The frequency at which the number of samples failed gives you a distribution of that strength of that material. So that's great. So now we've got this data. So let's say we're going to use that to design a bridge. Where do you think we want to, okay, so we've got data from 27 or 26,000 pounds per square inch up to, looks like almost 55, 56. So where in there should we design the bridge? If you ask your students this, they may say, well, most of them broke there in the middle. So right around there, around let's say 37,000 pounds per inch. So that's great. So every other time you drive on that bridge, it's going to collapse under you. So that's probably the wrong answer. So getting this kind of data, though, says, okay, I can run statistics on it. I can say, okay, give me a probability where this thing won't fail. And I can say, okay, running statistics, I could say, well, if I go, let's say, down to 27,000 pounds per square inch, if I take the area of this curve, 99% of the area is to the right of that thing. It's at a higher stress. So I have only 1% chance of failing at that level, at that stress or lower, or at that particular stress. That's not bad. That's better. You know, not only 1 in 100 chance of failing on you, but this is the kind of data you need to have in order to do your design. It's only one piece of it, one piece of the problem, but it's an important piece. So basically, this material strength becomes an allowable, and what we end up doing now is saying, well, let's take an allowable that's some statistically stiffing lower bound of all that data, and we'll run that data. I should have pulled this up too. This is one of our structural test specimens we use. This, you can do a very small materials test, or you can do a structural test. And this is a cross section here. You can kind of see what this looks like in cross section. It's eventually a piece of a wing structure. So this is a single. This is the skin right there, and here's a stiffener. And a wing will have multiple, essentially have multiple stiffeners over the width of the wing. So here's the wing. You know, the width of the wing is this direction. The length from root to tip is in that direction. And you essentially want to design the wing so it doesn't fail under load. In this case, this was a compression test. You see it failed. This is a composite design we're working on. This failed on about 50,000 pounds. This one little specimen. So right now, I guess the Boeing 787 is going to be the first large-scale composite airplane that flies, and it doesn't have this design, but this is a design that we're working on at Boeing that will be subsequent to the 787, we hope. But going from a simple material, you can go to a complex structure and use modeling simulation to actually predict how that will fail based on these simple material properties. Well, then getting back to the example, so we've got material properties, we've got the strengths. Okay, I think Juan mentioned this as well. What inputs go in there? Loads. He mentioned, you know, what are the loads, like the winds, things like that. All these variables that are loads, we need to understand what those are too. And they are actually governed by probability statistics also. This is showing a very large scale simulation of, in this case, this was the Ares 1 that was at one time going to be NASA's next launch vehicle. All right, let me move my microphone a little closer. So we go to understand what the loads on this. You launch this vehicle. We want to understand what the loads are, because that's a part of the problem too. You know, any kind of structural that you design with. Okay, any structure you design essentially designs because it fails because you have a load that made it fail. So we have to understand the loads. And the loads themselves are governed by probability statistics, and the stress due to loads are an important part of it. All right, so this is showing some of the simulations that were done back when developing this vehicle. What are your parameters? I think Juan talked about Monte Carlo simulations. Monte Carlo simulation essentially is you've got all your analyses are deterministic, but you have to have a way to vary your input parameters in some way that varies according to the statistics of your inputs. So in this case, we have a lot of data on wind profiles. So each of these little curves here, from going from the top bottom, is a different wind profile. And we know a certain wind profile happens with a certain frequency. And so that's one of the inputs to the Monte Carlo simulation of a whole ascent trajectory. Other parameter variations like engine performance. The engine may have a thrust of 100,000 pounds plus or minus a certain amount, and it can vary in there. So all these parameters that aren't 100% fixed, you understand what they are, an average and a distribution around that average, just like we had the strength. And those are all inputs into a Monte Carlo simulation, in this case of controls. Run that through there, and what happens is they find, you saw the footprint that Juan showed for landing. this is a footprint here of angle of attack going through a control system. So you essentially want all your extreme load, everything to be inside that ellipse there that shows that's again like a 99 percentile. 99 percentile, all your loads are inside that area.
What's the angle of attack?
Angle of attack is you're going into the wind. If you're going right into the wind, you're at zeroing attack. You go off 1 degree off the wind, you're at 1 degree angle of attack. That's at least a rough analysis of it. I'll let the guys in control folks here in the back go and talk about it in more detail. I'm a structures guy. But we do take that, it goes into a flexible model. So now all the dynamic models of the structure, which can vary and have bending and things like that, can give you loads. And based on that, we get all the stresses and deflections of a structural model. And for every instance of that Monte Carlo simulation, we get one result that shows you all the bending and deflections and stresses in that model. And we run another simulation that goes into Monte Carlo, another single wind profile choice, one choice of parameters, rerun that analysis. And you essentially go through this process of Monte Carlo, just a formal way of going through all these parameter variations in order to get some statistics on your outputs, which in this case are stresses and deflections. So that's our loads. We care about the stresses due to the loads. Okay, so I got part of this cutoff here. So basically, the stress due to the loads come from a structural model. I mentioned that. You've got a structural element model. And that's used to determine what are the thicknesses of all those pieces of structure. So if this is a piece of a structure, what's the thickness of this skin there? What's the thickness, what's the height or diameter of this little rod here, this cross section? So all those pieces all over your vehicle are designed to be the most optimal possible, to be the most weight efficient. And that's done by taking the structural model, the loads that are applied to it, and getting stresses. So basically, based on the strength allowables we talked about earlier, we can get the structure size to minimize weight. What's the minimum weight without failure? And you can do this all on the same curve. In fact, this over here, this blue curve here is like the histogram we showed on the strength. If you look at the loads and the stresses here, that's what this red curve here. So you can basically put them both on the same probability diagram or frequency diagram. In this case, we're calling it probability density. And so it's either strength or loads on this axis here. And so your strength follows this distribution on the blue. Your loads and your stresses due to loads follow that red distribution. And for every instance in a Monte Carlo simulation where your load is greater than your strength, you failed. And so you kind of see this little overlap area down there is kind of where you have to worry about, where strength could be worse than load. And you want to minimize that area. Well, one way to minimize that area is just to make sure those two curves are further apart from each other. So basically, if you can take the allowable strength, that's the 1 in 90, 1 in 100 times that it fails. The extreme load, let's say it's a 1 in 100 times we've gone beyond the load level that we care about. And we just separate them. We put a factor of safety between them. It poses a separation, so basically they stay away from each other. This area gets smaller and smaller, and we become a safer and safer structure. In fact, most aerospace structures are designed, not intentionally, because we use factor of safety, but if you actually calculated, they would fail 1 in every 10 million flights. So they're airplanes we fly on are extremely reliable because of this separation between those. So basically, a factor of safety imposes that separation between the strength and the unknown and the stress that you fly at to account for all the unknowns that basically could cause a failure, or that little blue overlap area. Okay, so let me move on. So we've talked about these things having probability distributions. We don't actually in civil engineering, there are some areas that they use reliability-based design methods in designing bridges and things like that. We don't do that so much in aerospace, although we're moving in that direction. But you can compute the reliability. I mentioned 1 in 10 million times you fail from that overlap there, and it's really that overlap area down the bottom. It's really the integral 1 minus the integral of the strength probability distribution. So take this distribution times that distribution, integrate it whenever the stress is greater than the strength. And that is actually a number you can calculate or use a Monte Carlo analysis in order to predict. And it is actually reliability. That's where we know, you've got 1 in 10 million times chance of failing in a structure. But we don't design, because one of the problems is you won't have insurance companies saying, I'll allow 1 in 10 million times this airplane to come out of the sky and fail. They don't. So once you actually give a reliability requirement, you've kind of opened the door for the lawyers to come in. But NASA, we actually certify our own vehicles. In fact, most of our vehicles are designed with much lower reliability. We actually fly the shuttle with approximately 1 in 100 chance of each flight it would fail. And you understand we've had failures in shuttles, so you understand that is low reliability. But our structures are still designed and for shuttle and other vehicles, very, very high reliability. So we're actually over-designing them from the point of view of all the other risk factors involved. So what we're trying to do within NASA is, even though we've had factor safety design in aviation for 80 years, really, it's been around for a long time, and it's evolved as we've learned more about materials and structures. In fact, the factor safety that's commonly used now is 1.5. 1.5 times your extreme load is your minimum strength allowable. Although NASA uses a little bit less than that, we use 1.4 instead of 1.5, so we're taking a little more risk, but not a lot. But they're very reliable. But for exploring space, we need to have other ways to predict our designs, to understand how to design for a case where we're not over-designing it from a strength point of view if we're going to fail due to some other reason that's got a much more higher probability of occurring. So we're looking at ways where we can look at reliability-based design as a standard practice and do that. But the challenge, as mentioned, there's the computer codes required to do that, the expertise, but also there's just the comfort level. As I mentioned, at NASA, we certify our own designs. We don't have any reliability like a commercial aircraft company does to worry about, but there's a comfort level still that people are a little concerned about. So what we did, let me move on, I think. This moves on to kind of what we did last year's mentorship. Last year's mentorship had 2 really, really good teachers, Joe and Jessica. They were from the Boston area. And they focused on putting together a lesson plan where they looked at structural strength. And I don't know if they've ever, I think they actually filmed some of their presentations they did. They did a really good job. We went to a structures lab, took popsicle sticks, and went to a test machine, fully instrumented, computer controlled, whole 9 yards, and they went through it and tested it the way NASA would have tested it. They couldn't do that in the lab, so they found a way to simplify that for the lesson plan, so they were able to do that. But we didn't spend a lot of our time doing that, to be honest. We spent most of our time doing field trips. This is your opportunity. You're here for 2 weeks. There is so much going on here at Langley. You walk past the lab and you'll see stuff going on there. You say, well, what's going on there? Or whatever field center you're at. Ask the people there. The people that you're working with really love to tell you about what they're doing. Their families won't even ask them because they figure it's going to. So basically, this is their opportunity to be able to tell someone about it. Anyway, so when you get with your mentors, you'll have plenty of time with your mentors to put your class lesson together. So I encouraged you and them to look at as much other things going on other than the thing you're focusing on, because that may lead to a lesson in itself. So anyway, that's kind of this is a great chance for enrichment. So that's kind of my message there. And when working with your mentors, the way it worked for me anyway is you guys do all the work. The mentors sit back there, and we're here to answer questions, the mentors, but 9 times out of 10, they're going to stand back and let you put stuff together and then help you, massage it a little bit. But this is really on you to put together the lesson, because you know what your students can do. You know what equipment you have in your classes. You know, we will way overcomplicate things if you have NASA do it for you. So please come to your mentors with, okay, here's how I want to do that. What do you think? You know, and they may be able to give you some good suggestions on how to change it. I think they end up using a bucket of water that they used to fill, and they figured, you know, on something a little bit bigger than a popsicle stick for their test, something they could do in their class as something that was meaningful. And then they just do a bunch of replicates and then the statistics of them. I think that's kind of what the lesson ended up being. And it's a very simple lesson, and you don't need 2 weeks to figure that out. So take the time you got here to really find as much as you can, and you'll enjoy yourself, and you'll do a great job. And that's all I got to say. Yes. Do I have an intro form? Okay. Well, I'm done. I apologize. I think I went a little bit over, and I don't have an introduction thing to read for Bezod.
Okay, that's fine. I'll do a little bit of that myself.
And if you want to talk to me outside of this or afterwards, I'm here in the field. Come by my office. We can talk. I can help arrange for tours. You got Jonathan Ransom here, who's one of the branch heads here, and he's got a great lab. He could have people show you around, and pretty much any facility here is like that. So please take advantage of it.